Hi guys, Mr. Gillen here, and in this video we are going to look at 3D Pythagoras. Now before we do that, I just want to quickly refresh your minds on Pythagoras' theorem, and hopefully you all remember that his formula, or the formula that we use, is c squared equals a squared plus b squared. And the most important thing that we always should be remembering is that C is the longest side. So if we look at these two quick examples, the first thing that I'm always going to do is I'm always going to label the sides. Now, if it's not blatantly obvious what side is the longest, then it will always be the side that's opposite the right angle. And then for the other two sides, it doesn't really matter what one you put where. So to actually find the length of C, I'm going to use my theorem, and I'm going to substitute in. So I've got 9 squared plus 15 squared. So I've got 81, add 225, which is going to give me 306. Remember, that's C squared. So to get C, I'm going to have to find the square root of 306, which is going to give me 3 root 34, which is 17.5 centimetres to 3 significant figures. Okay, so quick refresher, formula in, substitute into your formula, and then depending upon what the question asks for, it might ask for it as a surd in its simplest form, or it might ask for 3 significant figures or 4 significant figures. If we're trying to find a shorter side, if you have identified that C already has a value, then we're going to manipulate the formula. Remember, the formula becomes manipulated, so it becomes C squared subtract. In this case, I've labelled the 10 centimetres as A, so it becomes C squared subtract A squared. And again, I'm just substituting everything in. Until I get my answer. So b squared is equal to 300. I want to know what b is, so I need the square root of 300. And again, depending upon what the answer, or what the question, sorry, is asking for, we can go for as a surd in its most simplistic form, or I've given it in 3 significant figures. So that's a quick refresh on Pythagoras itself. What we're now going to look at is how we deal with it in a 3-dimensional world. So before we look at any problems or examples, we want to be familiar with terminology and concepts within a 3D shape that will then apply to 3D Pythagoras. So if we take the top here, the top of this cuboid, we've got a first dotted line up here, which is the side of the cuboid. We would refer to that, or I'll be referring to that, as an edge. Down the bottom left, we've got this dot that's on the point where 2 edges meet, or 3 edges meet in this case. We'll call that, or that is called a vertex. And the plural of vertex is vertices. Okay, so there are two pieces of terminology of maths language that we have to be familiar with. Now, as for the dotted lines, this is where the 3D element of Pythagoras comes into play. The first line that I'm going to bring your attention to is this dotted one down here that goes from the back corner down to the front corner. Now you can see that that is a diagonal line that runs along a face. If you can imagine a cuboid, then this bottom face, we're drawing a line that connects two opposite vertices. And we would refer to that line as a face diagonal. Now you'll also notice that we have drawn here another line on the side of the cuboid. That's also a face diagonal. And as you can probably see, we've got face diagonals on every face that connect opposite vertices. Now for this main dotted line, for this the bold dotted line that we've got, that goes from the top left or the back left down to the front right, that's moving through space. It's moving through the middle of the cuboid. So what we're going to refer to that line as is a space diagonal. Now, these are very important terms for 3D Pythagoras, and you need to be familiar with them in order to complete this topic. So let's look at an example then. We have got calculate the length of this space diagonal of this cuboid. And as you can see, we've already marked in one of our face diagonals, and we have marked in a space diagonal. What you might find in some instances is the question might ask you to find the length of the line connecting two different letters or two different points, so keep an eye out for that as well. But in this instance, we've just been asked to find the length of the space diagonal. So because I've got knowledge of what a space diagonal is, I've marked them in already. So I'm going to find the length of, in this case, PB, the line PB. So how do we do that? Well, the first step is to find the length of the face diagonal. We need the face diagonal in order to find the space diagonal. And sometimes what I find quite helpful to do is to take at the side the time to draw a small right angle triangle that I can fill in. Now, the triangle that I'm going to be working with, I've got to use almost my imagination to be able to see it, is going to be from D to B, and it's going to go along here. So that's my triangle here that hopefully you're able to see. So it's maybe probably better if I remove this drawing itself and we draw it round the way that we can see it to make it that bit easier for us. So I've got D, A and B. For the lengths of my sides, well, between A and B it's 8 centimetres, and for A and D I don't have a measurement, but between B and C it says 6. It's a cuboid, so I know it's going to be the same, so I can put 6 in there, and I'm left with trying to find DB. So I'm going to use my Pythagoras. I know that my longest side is what I'm looking for. So it's going to be c squared equals a squared plus b squared. Substitute my values in. And then, just like before, I need to work out what this missing side is. So c squared is equal to 100. C is going to be the square root of 100. So in this case, C is equal to 10 centimetres, which means that my face diagonal, or the line DB, is 10 centimetres. And that's my first step. Once you've found your face diagonal, then it's always a good idea to mark it into the diagram so that you've got that in there for yourself. And now we're going to try and find the length of the space diagonal. So one of the most important parts about this is being able to spot the right angle triangle. So there wouldn't be a point of finding the face diagonal if I wasn't going to use it. So my triangle is going to be from D to B, from B up to P, and then from P back down to D. My right angle is going to be in here. Now remember, it's a 3D shape on a 2D space, so it's not as easy to spot it, but trust me, it's in there. From there, again, I'm going to do almost the same process as step 1. I quite like to have my smaller triangle drawn out to make it easier for me to take out any measurements. I've worked out the length of D to B is 10 centimetres. From D to P, well, I know that's going to be 5 because I've got a measurement from AQ up at the front. From A to Q, I've got a measurement of 5. So I know that from P to D, or DP, is going to be the same length. I'm trying to find my longest side, so I'm going to use Pythagoras as normal. So I've got c squared equals a squared plus b squared. Notice that I always write out the theorem before I do any sort of substituting. So I'm going to have 5 squared plus 10 squared, which is 25, and 100. So c squared is equal to 125. I want to find c, so I need to do the square root of 125. Which in this case is 5 root 5. Or if the question asks for 2 significant figures or 3 significant figures, c is going to be 11.2 centimetres. So my space diagonal PB is equal to 11.2 centimetres. So that's my 2 steps. Find the length of the face diagonal and then use that to find the length of the space diagonal.